Wait statements are used to pause execution of the process until some condition is satisfied. Three variations of the wait statement are the wait on, the wait until, and the wait for. The wait on pauses the execution of the process until some trigger event occurs. So for example, if I say wait on A, comma B, then either A or B has to transition for that wait statement to be satisfied and the process to continue executing. The wait until uses some Boolean expression to pause the process. So until that Boolean expression is true, the process pauses. So here's an example. Wait until int is less than 100. So the process will quit executing once int drops below 100, then the process continues. And then wait for allows you to indicate some time expression. Once that time expression has that time has passed, then the process is allowed to continue. So I could say wait for 20 nanoseconds. Once the process gets to that line, we have to wait for the equivalent of 20 nanoseconds, and then the process is allowed to continue executing. The wait statements can be combined to form more complex statements. So for example, I could say wait until A equals 1 for 5 microseconds. What this means is that the process will stop at this line and wait until A gets the value of 1 before continuing execution. If 5 microseconds have passed and A has not reached the value or has not changed to the value of 1, then the process would be allowed to continue execution. As a note, wait statements have some limited usage in the synthesis environment, so it's always a good thing to do is to check your synthesis tool to see what it supports with regards to wait statements. Next, we need to understand how VHDL simulation works. By understanding VHDL simulation, we can also understand how synthesis tools apply these same rules to generating hardware. The first idea is the idea of the event. An event is a change in value, be it a signal value, be it from 0 to 1, x to 1, x to 0, any change in the signal is considered an event. Next is the idea of the simulation cycle. The simulation cycle is made up of wall clock time and simulation deltas. Wall clock time is any time the simulator advances from, for example, 1 nanosecond to 2 nanoseconds, from 2 nanoseconds to 3 nanoseconds. That's considered wall clock time. Simulation deltas are the executions that occur within within one clock time or simulation cycle. For example, if I have a process that changes the value of a signal, and that signal is another process is sensitive to that signal, then that process needs to turn on and execute. Let's say it changes the value of some signal, and there's a third process that's sensitive to that signal, then that process needs to turn on and execute. Each of those little iterations, each of those processes that are executing is considered a simulation delta, and they all take place within a single simulation cycle or wall clock time. So let's look at how this is done using the diagram. When you start simulation, all signals are initialized, and any process is sensitive to those signals begin execute. Once every process is done executing, that is when wall clock time advances. By advancing wall clock time, if any signals have changed, then any processes sensitive to those signals need to execute. Once those processes are done executing, then they will update signals. If those signals then cause other processes to begin executing, that is considered a second delta. Those processes execute, and then they update signals. If any processes are sensitive to that, then another delta cycle takes place. And that loop continues to execute until all processes are done executing within that simulation cycle. Nothing else is changing. And then at that point, the simulation cycle advances and wall clock time advances. So from that, when does a simulation cycle end and a new one begin? It ends when all processes are completed with their execution and all signals are updated. And the big thing we want to take away from this slide is that signals get updated at the end of the delta cycle, meaning this takes place at the end of the process, or if you have a wait statement in the process, once you hit a wait statement, that is when the signals in that delta cycle get updated. Why this is important is that the new value of the signal may not be available at the next line in the process. What we say when a signal gets assigned a value in an explicit process is that it's scheduled to be updated, but it is not updated until the process ends. So let's look at this example here. In these two boxes we have equivalent functions. On the left-hand side, we have two implied processes. They're both simple signal assignments, and so, say for example, A transitions. Then the first process turns on, executes A and B, and then a value gets assigned to C. Then, since C changes, the second implied process turns on and assigns the value to Y. Thus, it would take two delta cycles but one simulation cycle to execute the function. Now let's look at the code on the right. Here we have two explicit processes. The first process is sensitive to A and B. The second process is sensitive to C. If A changes again, the first process turns on and executes the sequential statements inside, which happens to be C gets the value of A and B. Thus, C gets assigned a new value. Because C gets assigned a new value, then the second process needs to turn on because it is sensitive to C, and then within that process, C gets assigned the value of Y. So again, on the right-hand side, two delta cycles to complete this operation taking place within one simulation cycle. Now in this example, we put both lines within the same process. So on the left-hand side, we still have the same code as the last slide, but on the right-hand side, we have a single process. Now in this case, they are unequivalent functions. Because this process is only sensitive to A and B, so let's say A changes. That means the process turns on and begins executing the sequential statements inside. The first statement says that C gets the value of A and B. Now remember I said C gets scheduled a new value, but the value is C is not actually updated until the end of the process. So when the second line within the process gets executed, this is still the old value of C. Only when the process ends does C get updated. So in order for Y to see the new value of C, it would take a second iteration of the process, meaning that A or B, one of the two would have to change again for that new value of C to actually reach to be applied to Y. So again, these two are not the same functions. On the left, we have one simulation cycle, two delta cycles. On the right, we would actually require two simulation cycles for this code to be executed. So to get around this, VHDL has the concept of the variable. Variables are only visible and declared within a process. They're represented by a separate operator, which is the colon equal. Now the way they're declared is very similar to the signal, except you use the keyword variable. And what is different about the variable is that they are updated immediately. They do not have to wait for the process to end for a variable to take on a new value. Thus, they do not incur a delay. They're essentially used as a temporary storage, so you can place a value into temporary storage and then use it somewhere else within the process. Everything about the way the variables are used and declared is very similar to signals, except the keyword is variable, the operator is the colon equal, and the behavior is different. Again, the signal are updated at the end of the process. The variables are updated immediately. But like signals, you can do bus assignments to them. You can pick off single bits to make assignments, and you can do bit slicing. So now, using variables, I can take the code on the right and actually make it equivalent to the code on the left again. So now I do have a single process again, sensitive to A and B, but this time, instead of making C a signal, it is now a variable. Notice it is declared within the process, so it's visible only within the process. So now if we look at the way the code on the right is executed, let's say A or B transition. The process turns on and begins executing. The first line is evaluated. C gets the value of A and B. This time, since C is a variable, it is updated immediately, so when the second line is executed, Y gets the value of C. It is actually the new value of C. So in this case, the code would be executed. Y would take on the new value within one simulation cycle, like the code on the left. So comparing signals versus variables. The operators are different. Signal uses the less than equal to operator. Variables use the colon equal to operator. Signals represent actual circuit interconnect or wires. Variables represent just local storage so that I can use a value somewhere else within the process. Signals have global scope, meaning that you can take values from one process and drive them to another process by means of a signal. With variables, they're only visible within the process, so their scope is local. Signals can only get updated at the end of the current delta cycle, either at the end of the process or once a wait statement is reached. The new value is not immediately available. With variables, they are updated immediately, so the new value is available for the next line within the process.